The quantum world exhibits many strange phenomena. I cannot possibly show them all. Rather, I will focus on just very few simple examples. I would like to start with an experiment which was actually first performed at my alma mater, Goethe University in Frankfurt. Two physicists working there, Stern and Gerlach, considered silver atoms. They heated silver atoms in an oven and created a beam of these silver atoms. Silver atoms carry a magnetic moment, and you expect from classical electrodynamics that a magnetic moment experiences a force and is deflected in an inhomogeneous magnetic field. So they placed around the beam a pair of magnets which create such an inhomogeneous magnetic field. And they wanted to study the deflection of the silver atoms by this inhomogeneous field. Classically, you would expect that the magnetic moment of a silver atom can have a continuum of possible directions. And therefore, you would expect on the screen a continuum, a continuous area where the deflected silver atoms hit the screen. Instead, Stern and Gerlach found that the silver atoms hit the screen at only one of two possible spots. When you investigate more closely, you can actually resolve the hits by the individual silver atoms. I'm not going to explain to you how this arises. It has to do with the quantization of the magnetic moment. Suffice it to say that this is an experiment on a quantum system which gives only one of two possible results. A measurement of this kind is also called a binary measurement. The Stern-Gerlach apparatus can be rotated by an arbitrary angle theta, and no matter by which angle you rotate it, it remains a binary experiment. Binary experiments exist not only for silver atoms, they exist also for photons. Photons are the quanta, the elementary constituents of light, or more generally, electromagnetic radiation. Nowadays, you can actually resolve and see individual photons. If you dim a laser enough, then on a screen or on a detector, over time, you can resolve the hits by individual photons. Now, photons too can be subjected to a binary experiment. Imagine a laser emitting a beam of photons, and then a crystal, or more precisely a pair, two crystals separated by an interface. This crystal or this splitter can be devised in such a way that each photon either passes through or is deflected. So the laser beam is split in two. Photons going in one direction are horizontally polarized. Photons going in the other direction are vertically polarized. And you can measure which way a photon went by placing detectors at the end of these beams, and then one of them will click. So once again, we have an experiment, a measurement on, this time, a photon, which can give only one of two possible outcomes. Only one of the two detectors will click. Here too, you can rotate the entire setup by an arbitrary angle, and it remains a binary experiment. I denoted the angle here by theta over 2, whereas in the case of the Stern-Gerlach experiment, I denoted the angle by theta. This is due to the fact that in the case of the STERN-GERLACH experiment, you have to rotate by 2 pi, so go full circle, in order to return to a setup which performs the same measurement. In the case of the beam splitter, the polarizing beam splitter, because it splits according to polarization of the photon, in that case it makes no difference if the interface is tilted in this way or in that way. Both correspond physically to the same measurement and they effect the same splitting. Therefore, a rotation of this splitter by pi is enough to return to an equivalent measurement. And in order to have, however, a uniform property of this angle theta, that as soon as theta reaches 2 pi, we are back to the same measurement, I used here theta over 2. So increasing theta by 2 pi means rotating physically by pi and means coming back to a measurement which is equivalent to the original one. Now we leave behind these two specific realizations of binary measurements and speak in more abstract terms about binary measurements. So let's imagine a source that can be atoms, photons, or maybe even something else. And the particles are subjected to a binary measurement which is characterized by some parameter theta. There are two possible outcomes corresponding to an upper beam and a lower beam. Now you can block out one of the beams, let's say the lower beam, and perform a second binary measurement on the upper beam. Now this first measurement determined whether as an individual particle was up or down. If you perform the same measurement again with the same parameter setting, then you would expect that you find the same result. You know, if I roll a die, I look at it and I see 5 spots. And I look at it again, I still see 5 spots. So in order to be a measurement, we expect it to be reproducible. So if we place now a second device at the same setting, then we would expect that certainly a particle that came in from the upper beam of the first device will exit the second device also in the upper beam. So a particle where we first determined it's up, we measured up, and we measure again, it will still be up. And indeed, that's what we observe. That's true for both specific setups that I mentioned, and it should be true for any reasonable physical measurement. If the second device is no longer at the same parameter setting, but the parameter setting is shifted by some delta theta, then we can no longer expect reproducibility. Then in general, the second device will split the beam again, and with a certain probability a particle will exit in the upper beam, and with the remaining probability it will exit in the lower beam. The probability for the particle exiting again in the upper beam is a function of this parameter shift delta theta. There are a few special cases where we can immediately give the probability. If delta theta is 0, then we are back to the situation where the measurement should be reproducible, and that probability should be equal to 1. If, on the other hand, delta theta is pi, then think of the STERN-GERLACH experiment. You have the two magnets upside down. So what used to be up in the first magnet is now down in the second magnet. So for sure, if a silver atom exits the first device in the upper beam, then it will exit the second device, which is upside down in the lower beam. So the probability that it will be again in the upper beam, that will be 0. Now you can measure all the probabilities in between by varying continuously this parameter theta, and in between there will be a continuous decreasing curve. Now the interesting thing about this function, the probability as a function of this parameter shift, is that it is exactly the same for the silver atoms in the STERN-GERLACH experiment, for the photons with the polarizing beam splitter, and in fact for any binary measurement on a quantum system. This is a universal function. Now, in the context of binary measurements, you find a number of peculiar features. First of all, consider this sequence of binary measurements. You have a source, and let's start with a measurement with parameter setting pi over 2. It splits the beam in two halves. Let's once again say we block out the lower beam and we subject the upper beam, the particles in the upper beam, to a second binary measurement with a different setting, theta equal to 0. Now, since these are different parameter settings, the second measurement will split the beam again. And let us one more time block out the lower beam. And then we place at the end a third binary measurement device, again at the parameter setting 0. Now, for the last two devices, reproducibility applies. They have the same parameter setting. So by reproducibility, we expect that all the particles which enter the last device should with certainty exit in the upper beam. And indeed, this is what you observe. Compare this to an alternative arrangement. It looks almost identical to the first. The only difference is that we flipped the order of two devices. The device with setting pi over 2 is now in second place, and the device which was formerly in the middle is now in first place. If the order of the measurements was irrelevant, then we would expect in the end on the screen or with our detectors, we would expect the same final outcome. We would expect that again all particles exit in the upper beam. However, this is not the case. In fact, the last device will split the beam once again, and the probabilities are 50-50. So, in the quantum domain, it is important in which order you perform measurements. The order matters. you can view this combination of a splitter and the subsequent blocking of one of the two exiting beams as a filter. You perform a measurement, a binary measurement, and if the outcome is up, then the particle is allowed to pass. If the outcome is down, the particle is absorbed, it is blocked, and it is lost. So, effectively, this is a filter. Now, consider this setup where you have first a filter with the setting 0, and then you have another filter with the setting pi. We said before that pi with the setting theta equal to pi, up and down are flipped. So if in the second device you have a particle coming in from the upper beam of the first device, it will certainly exit in the lower beam. And if you block that again, then no particle will be left. A screen will remain dark, or if you have a detector at the end, it will not click. In general, you would expect that each filter reduces the intensity of a beam. The filter performs a measurement and lets only a fraction of the particles pass, namely the fractions for which the measurement yielded a particular result. So you would imagine each filter reduces the intensity. The more filters you have, the less particles overall will pass, and the lower the intensity of the beam in the end. In fact, here we have only 2 filters, and that's already enough to eliminate all the particles. However, if you place in the middle a third filter with an intermediate setting, here pi over 2, then suddenly some particles will pass again. So it is no longer true in the quantum realm that the more filters you have, the smaller the intensity of the beam. Rather, you can increase the intensity of the beam by adding more filters. This allows you to do something which is called steering. You can have particles coming in and then subject them to a first filter. Let's say here you have photons coming in, and this is a polarization filter which filters out only photons with vertical polarization. If you placed after that immediately a filter that only lets photons with horizontal polarization pass, then none of these photons would pass and you would have darkness after the second filter. But if you place in between a filter which is rotated, let's say by 45 degrees, some photons will pass, and if you then place your filter that filters out the horizontally polarized photons, then suddenly some photons will still pass. So the more filters you have, the more light you get. This can be used to steer a photon which initially had vertical polarization to become a photon which in the end has horizontal polarization. So you can actually steer a photon, or more generally a particle, from one state to another state which originally would have been the opposite and would not have passed the first filter. Finally, I would like to show you one last phenomenon. Imagine again a particle source. In this case, let's assume these are photons. They hit a crystal, but this time this is not about a photon going either this way or that way. Rather, if one photon hits the crystal, this is the so-called nonlinear crystal, then this single photon is converted into two photons. So you have one photon coming in, two photons going out. And now both photons, both members of this pair of photons, are subjected to binary measurements with identical parameter setting theta. The peculiar observation is that no matter how you choose theta, if one of the photons is up, meaning it is detected in the upper beam, the other photon with certainty will be down, and vice versa. So the results of these two experiments are perfectly anti-correlated. And this perfect anti-correlation is called, or is a signature of a quantum phenomenon called entanglement. To summarize, I showed you a particular class of experiments on quantum systems, the simplest experiments that you can imagine. Experiments with only two possible outcomes. No matter which specific quantum system you consider, the probabilities for the respective outcomes, if you place two such measurements in a row, are universal. They do not depend on the specific quantum system under consideration. The order of measurement is relevant. Classically, it doesn't matter if I look at this presenter first from the top, then from the side, or first from the side, then from the top. It doesn't change my observations. But in the quantum realm, it does matter in which order you perform a measurement. Furthermore, in the quantum realm, you can use measurements, a sequence of measurements, a sequence of filters actually, in order to steer a particle from one state to another. And the more filters you add, the more intensity you can get. And finally, in the quantum realm, you observe perfect anti-correlations between two members of a pair of particles, which you can think about whether there could be a classical explanation, a classical description for these perfect anticorrelations. There's no simple classical explanation for that. And in fact, it's the signature of a quantum phenomenon called entanglement.